Okay, so finally, now we looked at the backward difference. What I forgot to mention is that the backward difference method is stable. Okay, so it's a much preferred method to the forward or explicit method. So this implicit method was much better. Okay, so that was a good thing. But now, okay, remember a centered first derivative approximation is much better error-wise here than either forward, as in our forward difference method, or backward, as in our backward difference method. Okay, so what we want to do is actually do a centered difference method. And this actually has a name. It's two authors' names, the people who came up with this. It's the CrankNicolson method. And so what we want to do is think of our centered, this as a centered difference. Now, in order to do that, what we do is we take that same u at j plus 1 I minus u at j I over our k or delta t thing. Now, but to make that a centered difference, what we do is we take our alpha squared, and I'll do the h squared outside here. But what we'll do is we'll do an approximation at both j and j plus 1 times and take the average. Okay, so what we have is we'll have our minus u sub j plus 1 I minus 1 plus 2 u sub j plus 1 I minus u j plus 1 I minus 1. Okay, so there is time j plus 1. Okay, we'll take that and we'll add to it. So I've got to put it down here. And I'll put this over 2, and I'll put this other one over 2. It's really both of them over 2 because we're taking the average. But we're going to do time at j, and so we'll have minus u sub j I minus 1 plus 2 u sub j I minus u sub j I minus 1 all over 2, like that. And so you see we're taking an average of the two times, which then says actually this is a centered difference for sort of u j plus a half. Okay, that's the idea in this CrankNicolson method. Well, and again, all you do, I say all you do, these are unknown, okay, because they're the new time. These are the old time, these are known. I'll put all the unknown stuff over on the left. This is known. Put all the known stuff over on the right, and I'll get a bunch of equations. And again, I get, and the way I do it, I'll get n plus 1 linear equations. With n plus 1 unknowns. And there we go. That's the idea of the Crank-Nicolson method. I'm not going to have you all, do all the Taylor series work and so forth to get this. Mostly, though, I want you to see the idea, so that you get the notion of, why Crank-Nicolson? Well, because it's a centered difference. So now all of a sudden, our convergence is order of k squared and h squared, instead of with the other two, order of k and h squared. So see, this is the better thing because it's a centered difference. We think of it as a centered difference. And, if you take a numerical partial differential equations class or something like that, then you actually do the proofs to, to show these convergences work and that they're stable and so forth. But the Crank-Nicolson is a very nice method for this. And definitely as h and k get smaller, much more accurate method. So that is the idea of the Crank-Nicolson, doing a centered difference and a very stable method, very, very quick conversion method. And so that's what we implement for us. All right. So that does it for our various difference methods.